Welcome to Insight Builder channel, large language model automators, Python experts, and my dear friends. 4-bit quantization demystified with transformers, a solution for training and reducing model size. Challenge solved. Compressing the model size. The question, why to compress the model? So let us take a look at this particular figure that has been provided by the Hugging Face blog, and which was again created with the help of a lot of other open source models that is available out there. We see that the large language models are literally large. You see here this particular data that you have seen here. In order to make an inference on the Bloom, this particular model, that is open source Bloom model, which is 176 billion parameters in size, it will take 8 GPUs. That is 880 GB A100 GPU, which costs around 15K US. And if you are planning to fine tune this model as it is, then you will need 72 GPUs of the same specification, which is 9 times the value of inference. This is extremely huge investment. So even if you consider that most of the corporations may not be able to, even corporations may not be able to invest this much on a model. When that is the case, what will happen if it is going to be a 540 billion parameters, like the Google's Palm, the Bard API, which is getting, which you are able to use it runs on a model that is 540 billion in size. In compared to these, GPT-2, the original model that was released as open source by OpenAI, is just 1 billion in size, which is way more smaller. And you guys must have already played with GPT Neo X. So we can clearly see that the model sizes increases with respect to the number of parameters the model has. And also the second factor is the numerical format or the data type of these parameters. So the idea of compressing the model has two reasons. One is to reduce the memory footprint, and the second is to allow the masses to use the model, meaning allowing the regular user to work on consumer level GPUs and create inferences or make inferences on the model. That is the primary objective, and that's why we want to compress the model. In order to compress the model, the process that we are going to use is called as quantization. In order to go into and understand what is quantization, we have to understand a bit about the data types. I'm not going to delve really deep into this. I'm just giving you this particular slide here, that higher floating point precision plus more parameters equal to bigger size of the model. So this is the overall idea, that if the floating point precision is higher and the number of model parameters is high, then the model is going to be bigger. Now if you are going to reduce the floating point precision, and if you are going to make it a different kind of a data type, then we can reduce the model size. That is the idea of quantization. So here I have given some background of the various types of data types available. So it starts from FP32, goes to TensorFloat 32, FP16, BFloat 16. These are all various kinds of data types that is available in the machine learning ecosystem, and these data types have been created by various organizations. Like BFloat is BrainFloat, created by Google Brain team, and we have TensorFloat. It is introduced by NVIDIA, and there is a separate blogs. I'll be giving the references to that in this particular presentation. You can take a look at that. And also I got this information. So you see the point. You as you might be a developer, or you might be a senior leader or a business manager who may not be really interested in all this nitty-gritty details of computer science. However, the reason why I am insisting or sharing this specific information is that as a business, as a owner, or a person who is responsible for using the technology, having a having a base knowledge of these kinds of information is going to give you an edge. So what is the edge that I'm talking about? So the key point here is that the most of the models that is available out there in the open source or as well as in the closed source is either of these uses either of these types of data types. And most of the models use FP16, and which can store up to 65,500 plus or minus 65,500. That is the maximum range of this FP16 floating point data type. However, when you change the floating point data type to FP32 or BF16 or TF32, then you see the number which the data type it can represent is very, very huge. You see this TF32 and FP32 as well as BF16 can go up to 3.4 e to the power 38. That means 3.4 followed by 38 zeros. That is a huge, really huge number. When compared to them, FP16 is just 64,000 or 65,000 maximum, plus or minus. What is happening in this case is that when you are trying to fine tune the model, or when you are trying to create the neural network will be having random numbers. So you guys might be totally new to neural networks. You guys may not be even familiar about machine learning. So all you need to know is that it's kind of a function. It's kind of a matrix. Yeah, that's a good thing. So you must have seen matrices in your class 12th or class 10, where you must have seen matrices as rows and columns. So same way. So neural networks are much more complex and complicated matrices of numbers which can change based on the input and output you give. So this is what you guys have to understand about the model as such. Next thing is, what you need to understand about the model as a next step is that the model is a storage of functions. So the model that you're talking about, so for an example, this Bloom or Palm or YAM, whatever model is there, it actually stores the functions, meaning it stores the instructions and its results. So if I say a plus b equal to 2, a plus b is actually addition of a and b. This is a function, and this particular function and the way of adding two numbers gets stored inside this model. Model is kind of a storage repository of functions, and these functions are written or created using numerical values. That is what we are talking about. So this is what you guys have to understand at the top level. And so what is happening here? So why am I actually explaining all these things to you? That if someone says that okay, these models can become artificial intelligent, or if they can take decisions by themselves, actually they cannot. They're just like your hard disk or like your pen drive, which stores your data. It just stores the functions, nothing else. And if you ask for those functions to be executed, then these models will execute it. So you are required to be there always. So keep that in mind. At least for now, these models are not going to run by themselves. Okay, someone has to be there to make it to run. And these are the various details about these data types, and also a basic introduction about neural networks. Right? Let us go forward. When it comes to this is the key point I was talking about. So when you are actually using the BF16 or bfloat16, then you'll see that Bloom 176 billion will be 352 GB in size. 352 GB in size, that too for 176 billion. So think about what will be the size of a 540 billion parameter palm. It will be extremely huge, right? And think about loading all those weights or the parameters into a GPU and trying to run it. It's going to take you a lot of time. Now what is happening is, the key point here is that whenever these models are created, as I was explaining, models are matrices, right? I was explaining to you in the previous slide. Whenever they are created, the numbers are stored in FP32 data type. But when you are trying to get the model to reply to your question or to create a text, then what happens is, even if we use FP16 or lesser data type, even then the inference was better. So this was something that was found by the Hugging Face team. When Hugging Face team had worked on Bloom model also, and they had been working on their own models, and they were the they were the team who actually started discussing about quantization. Now, I am still not touched the quantization, so let me come to that in the second step. So all these pictures I have taken from the blog. Let me go to the browser for a moment. If you guys are new to Hugging Face, if you guys are new to natural language processing or vision models, etc., I have a separate videos on all these tasks and models. Take a look at that. You will get a good idea, a good overview. I will not be delving directly into technical aspects because my audience are pretty wide. So I try to provide the challenge, and then I try to talk about how a particular model or a particular concept, particular library in Python ecosystem solve that particular challenge. That is the formula that I follow for most of my videos, or almost all of my videos. So you can take a look at that. Even if you are completely new to computer science, you will be able to manage to understand. That's the primary goal, and I hope that you will learn a thing or two from this particular series. The reason why I came to the browser is to talk about this introduction of 8-bit matrix multiplication blog. So this is a very lengthy blog, and from this blog only I have done this presentation. So I have gone through the blog, and I saw that additional information can be added onto this so that people like you can understand this important concept very easily, because you might or may not do the implementation, okay, but you need to know what it takes to implement something, so that when someone is implementing it for you, you can actually understand the challenges. And also, if someone says that okay, this is very simple, at that time also you will understand okay whether this is simple or not simple, etc. So all those things will be covered in this particular video. Let us proceed. So now we have spoken about the challenge and why we have to reduce the size of the models. And we have seen that by changing the data type of the parameters, how it is getting stored, we can reduce the size of the model. So if you reduce it from 2 bytes to 1 byte, then this 352 GB will become 176 GB, right? That is what we are targeting. And the 8-bit quantization is about that only. So we convert the FP32, which is actually of a higher number. It takes around 32 bits basically. So 32 bits is 4 bytes. So each byte will contain 8 bits. So it will be 4 bytes of memory in your RAM. So yeah, this is the key point. So everybody uses random access memory in some way or the other. Whether you are using your smartphone, whether you are using your laptop, you must have always faced the problem of Chrome slowing down your laptop, right? So you must have seen you have opened some 20 different tabs and suddenly your laptop slows down. Or sometimes even when you start your laptop, it is very slow. Because this happens because if your RAM is if your memory is completely filled with lots of programs, and that time your system slows down. Here, the model itself is going to go and sit inside the RAM, and each partition in your RAM is going to be 1 byte. So one parameter, meaning in this 176 billion parameters, one parameter is going to take a space of 4 bytes. Okay, so think about it. It is going to take 176 billion parameters is going to take 4 bytes. Then what will happen? So it will become 176 into 10 to the power 9 multiplied by 4. That is going to be twice this value. That is almost 700 GB of random access memory, which is insane, right? Who will have 700 GB of random access memory? It's pretty rare that someone has that. So then the concept of the GPUs came into picture. Even in case of GPUs, as I was explaining to you, each of these GPUs 80 GB has 80 GB of VRAM, that is visual RAM. What I mean to say is these GPUs are meant for processing visual details like matrices and rendering your videos, rendering the 3D graphics, etc. And we are going to use that visual RAM of 80 GB in size into 8. That is almost 640 GB of RAM is available there. So you see what is happening in this place. So the entire model has to go and sit inside the visual RAM. It's not the hard disk I'm talking about. So people, if you are from the if you have been working with the laptops, computers, Intel processors of the last generation, then for us, for people who like me, even a hard disk that is 500 GB of size was pretty rare to come across. But nowadays it is pretty simple to take a look at entire GPUs that is of size 500 or more than 500 GB of visual RAM. So it's a huge difference in thinking. That is the reason why I'm sharing this information with you guys. So if you think that working with large language models is very simple, it's like working with the regular applications that is running in your laptop. No, it's not the case. That's going to take a huge amount of effort, and it's going to take huge amount of memory space and resources. And think about 15K per 180 GB GPU. So 15K into 8 is going to be almost 120K US dollars. That is just for inferences, and I'm not even talking about the motherboard that you need to use for loading all those GPUs and then loading the software, I mean, it's a huge complex activity. Keep this in mind when someone is, and there are lots of open source, not open source actually, there are lots of cloud services that are getting created around this particular bottleneck, that is the resource bottleneck, where like Modal is one of the discussion that I was having. If you go back to the browser, I have been discussing about Modal recently, which helps you to load these kinds of models into the GPU inside the cloud. And it doesn't stop just there. So they have a very intuitive Python library called Modal Client that helps you to abstract the entire hardware allocation of the cloud. So they have done a really good job. So take a look at that if you are curious about the resource challenge that I'm talking about. Okay, now I have actually put the effort in telling you why this is an important activity, why quantization is important. Let us actually move to the next step. So quantization is basically rounding the numbers. Yeah, so you must have, if you are from accounting or if you are from a business background, we always round the numbers. Like for an example, if there is 1.5783, then we always reduce it to 1.6. So 1.578 can be rounded to 1.6. Same way, what is happening here is that when you are converting the higher precision number to a lower precision, that is a 4-byte FP32 to 8-bit, that is 1 byte number, then you are going to reduce the number of decimal spaces. And there are a couple of ways to do that. I'm not going to show you or dive deep into the algorithm here. I'm just going to tell you the algorithm. And in fact, even the developers or the programmers with whom you will interact with will not actually even think about these algorithms, because this is all done by the researchers who are working at Hugging Face and various organizations in research organizations and also in research institutes. They come up with all kinds of these data types, algorithms to work with the models. However, as a developer or as a programmer or an application user, learning this idea is very important, because you should know the basics of how the internal system is working. Like for an example, you might be a person who is running the business, but you still need to know how the cash flow happens. You still need to know how the profit occurs, right? You have to know the formula that revenue minus the cost is going to be your profit. So that is what I'm trying to talk about here. So as a user, you are understanding this particular idea will help you to decide better. So this is what quantization is all about. It's just going to round from 4-byte FP32 to 1 byte. This is what is happening, and there are a couple of methods to do that called 0 point and absolute maximum, etc. So you can take a look at that. This particular blog actually goes detail about that. So they explain a lot of things, and that is one of the reasons why you see this particular blog is extremely long. Okay, and after I went through that, I felt, okay, most of you may not have actually gone through that because of the length of the blog. I felt, okay, let me create a video on top of it. At the end, there is going to be something interesting also. We are going to run an example and to show you how is the difference. And so this is all is happening. And in the meantime, Hugging Face team had already, as I was telling you, Hugging Face team had seen this particular challenge and they had started working on this quantization challenge. They had introduced LLM.int8 implementation inside the Hugging Face Transformers library. If you guys are new to Hugging Face Transformers library, sorry about that, then I would suggest that take a look at this series of videos where I discuss about the datasets, metrics, evaluate library, and agents, transformer agents, and transformers inference pipeline. So all these three videos discuss in detail about using transformers library and the ecosystem around the transformers library. Let us go back to the PDF. You might be thinking that why I'm introducing all these videos, because all those videos are linked together. Once you understand those videos, I am not making an entire course as such. I am trying to provide the information that will solve a particular problem. But most of the time, one particular problem is going to lead to other additional challenges for you guys. So that's why I'm sharing you those videos. I hope you like it, and do leave a like about these videos, and do share it with others. The point is, these technologies are quite new, and a lot of people, especially who are not from computer science background, not from tech background, have a lot of confusion that when they are planning to invest, when they are planning to learn or upskill themselves, it is better for them to understand these concepts and decide whether they will be ready to invest their time, invest their effort in learning and mastering these skills. Do subscribe to my channel for further updates, not just on large language models. I cover various topics related to Python as well as open source ecosystem as a whole. So let us continue with our discussion further. As I was talking about this LLM int8, the process, the algorithm is also provided. You don't need to worry about this algorithm. This is getting implemented inside the transformers library. I'm just giving the algorithm here because if you guys are from the tech background, you can take a look at that. You can use this presentation as a reference, but I'm not going to discuss about that. Okay. This is where you guys will be interested in. So how are the results? So how do the quantization models fare compared to their regular model? Here you see that both quantization model as well as the regular model have zero degradation, meaning their accuracy is not reduced. Even if you even if you do the quantization, that is from 4 byte to 1 byte, the accuracy or the output of the model has not reduced. And the most important point is the speed of inference. Unfortunately, the speed of the inference for smaller models is slower for quantized models. So you can see that here. So here you see for this 11 billion model, that is T5 11 billion model, you see inside the T4 GPU, the speed is for the regular model is 1.7. But for the quantized model, that is int8, is 5.3. So it is actually higher. So it's almost 3 times higher for the inference time. This is one of the challenges. So here you see it is done on single T4. This is done on 2 T4s. So take a look at that also. So there is a difference. So here it is running on single GPU, but here it requires 2 GPUs. So these are the difference. And take a look at the Bloom 160 billion. So here they have compared it with the 8 A800s and 14 A100s. So A100 has 40 GB as well as 80 GB versions. So that is what they have compared. These are the and yeah, you see this has actually gone into out of memory. OOM means out of memory. So these are the outputs that has been given by the Hugging Face team in their paper LLM int8. So you can take a look at that also. And okay, the second point one of the challenges is that 8-bit tensor cores are not supported on CPUs. So that means that we cannot actually use this quantized model to run on CPUs. It's not going to be possible because it doesn't support our CPUs. The regular CPUs don't support the tensor cores, meaning it will not support these data types. So at the end of the day, as I was explaining to you, the parameters, the model parameters have to go and sit inside your RAM. And if your RAM is unable to take these FP32 or TF32 data types, then your RAM will not be able to, keep it. It cannot actually store it. So it will actually error out. So your regular CPUs will not work on this. But the graphics cards that is getting released by NVIDIA, so these are the various graphics cards, that is Turing and Ampere series GPUs. These GPUs actually support these tensor cores. And yeah, Google Colab GPUs, like especially NVIDIA T4 GPUs that I've been using extensively on all my videos, support these models and the data types. I hope that I believe that you guys have got some good idea right now. So here are the couple of references that I used. So if you click on this, it will take you to the reference. So here is the NVIDIA blog on TensorFlow 32. And here is the Hugging Face blog that I was using this presentation to create. And this particular Medium article is extremely useful if you want to learn about the various data types. And finally, we have the paper released by Hugging Face team, Mr. Tim Detmers, LLM.int8. So this is one of the papers that this particular blog refers to. And what are the inferences and inferences and future improvements that we can get? So first and foremost, a faster inference for the smaller models is something that they have to work on improving. Support for int8 on vector cores. So this is something which is available in the earlier generation GPUs, not the recent one. The earlier generations have vector cores, the recent ones have tensor cores. So this is one more thing. So these things will be useful if you're a developer, or if you're a enthusiast or if you are already a machine learning engineer who is trying to improve your knowledge. So this is a good place to learn. And as I was telling, CPUs don't support 8-bit cores. So one more improvement will be to make the models support CPU, and scaling this idea for vision and audio related modalities. So you guys must be aware that the models are not only in text, it can be in either audio or video. You guys must have already seen the image related models like DALL-E, Stable Diffusion, etc. So this particular point is talking about that. Let us proceed further. Now comes the interesting part, the part where I like the most. So what we are going to do is we are going to practice what we learned till now. And you might be wondering, Kamal, last 27 minutes you spoke a lot of things, but all we are going to do is these 3 steps. Yeah, really, most of these things you see here, I explained it for you guys to really understand the steps or the details that goes inside the quantization process. When it comes to really implementing it, Hugging Face team has done a really good job in abstracting all the complexities, especially this step. They have completely abstracted it, so you don't need to think what is going on. All you need to know is what kind of parameters, arguments you need to use inside the transformers library, and also a couple of libraries you need to import. That is what we are going to see. I believe that you will actually have fun for another 5 to 10 minutes. With that said, let us go to the browser. The example that I'm talking about is available at the bottom of this particular blog at the end of it. So the blog actually goes on and explains a lot of things. You can take a look at these 2 collab notebooks, which also I have placed it in my particular repo. The same thing, I have copied it so that if you guys want, you can use this also. I'm closing this right now so that I can get some RAM space, and I'm going to reconnect. This is the collab environment. You can import the notebook, or you can open the notebook if you already have it. And what I am going to do is it's connecting here. Let me zoom in a bit. Okay, here I will just run through the code. By the time it initializes, let me run through the code. Here, what we are doing is we are going to do some magic with bits and bytes and accelerate. So these are the 2 libraries that is required if you are going to run the model, the transformers model inside the GPU, and also if you want the model to be quantized to 8-bit. So for that, you need these 2 libraries. So go ahead and install them. Once you install it, it will take a little bit of time. So in the meantime, we can check. So this particular cell helps you to check whether you have this particular instance has a GPU. So we can see that this instance has a GPU, so you don't need to really worry about it. But still, let me run that point. And the model that you're going to work is BigScience/Bloom. This is BigScience is the repo owner, and Bloom is the model name, Bloom 3 billion. And we are going to execute that. Okay, so what is happening here is that we are going to get the tokenizer of the model. We are going to use the model generate using this particular code. And for this model generate, the model is taken from outside. So let me show you how it is being done. Why it is being done like this also I will explain to you. Now, first and foremost, we are going to use the 8-bit model. In order to get the 8-bit model, let me close this so that we will get some space. In the regular, okay, let us first explain the 8-bit model. So this pipeline class you are going to import from transformers, and inside the pipeline class, you are going to give this model parameters, model KW args, key value args. So arguments, if you give that and if you give the name of the model, what will happen is the pipeline will go to Hugging Face Hub and it will download the model. The entire model will get downloaded to this Google Colab environment. You can see if you go here, you can actually see the size of the available hard disk space. Or if you actually go here also, you can see the size of the RAM that is getting used. So currently 26 GB of RAM is being used out of 78, and slowly you will see that it's increasing. And also later, once we start doing the inference, you will see the GPU rise up to 7 or 8 GB. Okay, so let it download. It will take a bit of a time. I think it will be done. It's just 6 to 7 GB. And once that is done, what I'm going to do next is, so pipeline transformers class will do differences simply by calling the pipe, simply by calling the text. So if I click on this, so after this particular model is getting loaded, and if I click on this, if I execute this particular cell, you will see that you will see this particular output. Hello, my name is John and I am a student at University of West England. I am currently studying for. So how this output came out? The text is inputted here. Hello, my name is the prompt, and the max tokens is 20. So let me actually increase the max token, and let me actually keep it in a separate cell, because if I run this cell, it is going to again, let us keep it separately. And let us, I need to actually rerun this. Let me check it. Special tokens, output tokens. Let me rerun this, and let me also model name max new token. So I have to rerun this also. Anyway, the model is downloaded, so I'm just changing the max tokens, so it should not actually create any issue. And once it is done, let us actually do the inferencing. This particular step where I execute the pipeline with the model is called as inferencing. So the model is already loaded, and I am giving the prompt and I am asking for the output. So that is called as inferencing. And so there are two ways to do that. You can actually use the auto model for causal LLM and auto tokenizer. So you see here now, earlier it came up to this point, but now it has increased. A BSc in business management, and I am a keen golfer and have been playing for over. So it is actually increasing the number of tokens. So you can actually play with this. Also, you can use this classes. So in transformers, there is auto model class for that will load any of the model if you give the name. So it is called as auto model class for causal LM. So language model, LM is language model, and auto tokenizer. So you can use this, and again, you see that you are using this generate from model. That is the reason why this model is provided as a argument in this function. You can give other models and check it. So here, the model is initiated as a pipeline. Here the model is initiated using the auto model for causal LM, and again we are using this parameters. You see this device map is auto and load in 8-bit. So that is what we are doing, and again the output will be same. Let us execute this. Okay, this is going to create an error because I did not execute that. Let us see. It is going to create an error. Let me execute that. and model 8-bit is not defined. So let me execute this, and next we can also change it. Now what is happening is, when you say torch dtype equal to auto, so what will happen, this will go back to the regular FP16 model. So when I say model native, this is the regular FP16 model, and this particular code is going to compare both the model native and model 8-bit. So it is going to compare both of them on the memory footprint, that is the memory it takes inside the GPU. That is what it is going to compare. And you see that you'll see that anyway, eventually you'll see that the native model takes the native footprint. Here is the native footprint, FP16 model, it's around 6 GB, while the int8 takes only 3.5 GB. So it's almost 1.6, the native model is 1.6 times higher memory than the int8 model. So you see the benefit, right? And I was telling that it should be at least 2 times or more, right? This is the case when the number of parameters increase. So for here the explanations also provide that for 3 billion parameters, this is the 1.65 is the benefit, but when it goes to Bloom 176, then there is a gain of almost 1.96 memory footprint. So that is what the Hugging Face team has also shared. Here is additional steps that they have asked us to take a look at. You can actually play with this. It talks about 8-bit threshold. The threshold is depending on the rounding error that we are talking about. I'm not going to dive deep into this right now. It's not important for us at this point of time. If you are actually researching on improving the model output, or if you are thinking about the model accuracy is a little bit higher or lower, you want to play with it, then you can actually work with the parameter hypertuning. With that said, we have come to the close of this particular introduction. Sorry about the disturbance. I believe you have learned a thing or two about quantization, the reason why we have to quantize, and what are the benefits and what are the cons of quantizing the models, and the background of what is quantization and how it is being done. I believe that you will like this particular discussion. Do leave a like and share it with others, and subscribe to my channel for further updates. With that said, I would like to leave this video with 4 words, that is practice, 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 practice. See you guys. Have a great time.